Let's say we have a series of measurements, and basically I'm going to take set 1 from uncertainty, the pre-work, uncertainty and significant digits lab. I'm just going to take set 1. And I have a list of 20 numbers there. So first off, finding an average is easy enough. If you're using Excel or OpenOffice spreadsheet, or I think Google Docs uses the same one, you'd have average and then you'd have the numbers in between. And so I guess it'd be from B2 to B21. And you come out with an average of 25.7295. Now, not all of those are significant. We have all of the numbers that we're adding together are 4 significant digits, or to 2 decimal places, which is more important. So the 2 decimal places, because you add them all up there, and so the significance is to those 2 decimal places. And so really this should be written as 25.73 is the average. However, we do want to keep those for future analyses. Standard deviation is you would find the difference between each of the numbers. So for example, 28.99, 20.54, 27.09. Those are the first 3 numbers in the set. You would subtract the average from it, 7295, and you would come out with a number. Now, if you did not do anything else and just found the average of those numbers right there, you would end up with 0, because you have the average, you have just as much above that as you do below that. And so what they do is we square them. We find the average of the squares, sort of. One other thing that we do need to do here is we don't actually find the average of the squares. We find the squares, we add them all up. So we get the sum, and then we divide by 1 fewer than the number of numbers that we have. So in this particular set, there are 20 numbers. And so I would divide by 19. Now don't forget, these are squares here, and so I need to do a square root to get it back into, in a sense, the original units. Now the simpler way of doing that in Excel or OpenOffice spreadsheet, and probably Google Docs, is STDEV and then B2 to B21. That would handle the standard deviation of it. There are other standard deviations, but that is the one that we want. And now uncertainty is you take that standard deviation, and I'm just going to use sigma for it. Now, there are 2 symbols for standard deviation. There's the sigma and there's the S. One of them is for the population and one of them is for a sample. The difference is that population is you've taken a look at everyone possible, as opposed to just taking a sampling of it. Because you've taken a sampling of it, this is why you divide by 19 instead of 20. And there is some logic behind it, is that you've lost a degree of freedom because you're basing it upon this average, which is based upon the numbers already, but you can get into the weeds on that one. So to find the uncertainty is we take the standard deviation and then we divide by the square root of the number of numbers that were involved in that. And so that gets you the uncertainty. This is at the 68% level. To get it to so in other words, k is equal to 1, looking at some of the other literature. If we want k equal 2, this is the 95% level, so 95% confidence level. So you would take this number and then you would just multiply by 2. So technically this would be k up front. And so the standard deviation should be 3.932, and then there's a bunch of other numbers after that. If you're doing this in Excel, or you're doing it on a calculator, or however you're doing it, keep all those numbers there. You take that, divide by the square root of the number of numbers involved. Now what the uncertainty is telling you is that I've got this sample population here. I don't know what the full population is. I just have a sampling of it. And so if I did a histogram, I have discrete points here. There might be one that's a little bit, just by statistical fluctuations, I might have one that's a little bit off, but I'm not going to have that just absolutely beautiful Gaussian curve. And so in order to figure out the average of the Gaussian curve, If everything is done perfectly, then, well, the average we have here is the actual average of the entire population. This is just the average of the sample. This is not the average of the entire population. And so to offset that, the question is, how close are we, is this, to the actual average? And so that's what the uncertainty is telling you. So with that being 3.932 with a bunch of other numbers, my uncertainty for the 95% confidence level, 1.75849246. I'll put a little 2 down here. I don't know if that's the official notation, but I put a little 2 down here just to indicate that's for k is equal to 2. That means that I have a 95% confidence that the actual average is equal to this plus or minus that. Now, at some point we need to bring significant figures into it. Again, this is out to 2 decimal places. Ultimately, this is going to be out to 2 decimal places. Now, there is a whole bunch of funky stuff that goes on in that, and I could spend probably an hour going into that level of detail. But when dealing with something like this, that's where we're working on it. I have an average of what I would finally record as 25.73 plus or minus a standard deviation of 3.93 with an uncertainty, so this is the standard deviation, and the uncertainty being 1.76. So this is an indication of the spread of the data, that roughly 2/3 of the data will be within that value of this. And this number right here is an indication of how close the average is to the actual average of the entire population.